Hello everyone. Today we're going to discuss more how to do vector addition, but instead of from a purely graphical method where we draw everything to scale, right, or use a grid that's to scale, right, we're going to talk about how we can do this computationally with just math. So let's do an example here. Let's say I am adding three vectors together, which I am cleverly going to call them A, B, and C. So notice I want the vector sum of those three vectors. You can tell I'm adding them, of course, because I'm drawing them head to tail. Well, the resultant of that, whatever these are, whether they are displacement vectors or velocity vectors or other kinds of vectors that we'll talk about throughout the year, right? I would still add them the same way, graphically speaking, and my resultant, my net effect, would always run from the tail of the first to the head of the last. So I'm going to call that R in this case. So since this is vector algebra, we can't just add the length of A to the length of B to the length of C. It doesn't work that way, right? But we run into a little problem here if we're going to try to calculate it. Now, if I had drawn this to a perfect scale, and it is drawn to a scale in my PowerPoint, but if you didn't draw it with a ruler and a protractor or on a grid or something like that, then how could we do this? Well, wouldn't it be easier if we could take this vector diagram that we drew and change it a bit? What if I moved C down there and B over to here? Can I do that? Can I just move these around? Well, look at essentially what I've done. I now have A plus C plus B, right? Vectorially speaking. I've added them head to tail. Well, does it matter whether I add A plus C plus B or A plus B plus C? Right? This is what I've done. No, because we already proved that vector addition is commutative, so the order doesn't matter. So I can take a vector diagram that looks like this and make it look like that. And once I do that, well, now the trig just becomes a couple of basic things like a Pythagorean theorem, where I add up the lengths of A and C squared plus the length of B squared, take the square root, that'd give me the magnitude of R. And then if I want to angle at the tail always, right, of my resultant, so I can name it, whether that's with cardinal directions or counterclockwise from zero notation, I would use an inverse tangent of opposite side over adjacent side. Right? Opposite over adjacent, inverse tangent. Be careful when you're plugging this into a calculator that you're putting parentheses around these so that it takes does the division before the inverse tangent, right? Got to get the order of operations correct. And then we'd get an answer that we could name. So again, our tact here was to take a kind of a weird vector diagram and turn it into one that was easier to do the math on. That ended up being a vector diagram in the shape of a right triangle. And we could do that because vector addition is commutative. But what if the diagram was or the vectors were a little more complex? What if I was adding A to B to C, and I wanted my resultant going from the tail of the first to the head of the last? Well, now I can't just move or change the order and end up with a vector diagram that's in the shape of a right triangle. So what could I do? Well, remember our latest work was we learned how to take a vector at any angle and break it up into perpendicular components. For example, we could take B and resolve it into B sub x and B sub y. Right? This plus this is B. And we could put positives or negatives on there for directions like we did in the last worksheet. And once we've done that, now couldn't we move the parts around like this? Gather up all the x ones and gather up all the y ones? Notice we've gathered B here, but we've done it in parts, right? In components. And once we do that, we have a vector diagram that's in the shape of a right triangle with the same resultant. So watch that again here. So we start out with looks like a fairly complex situation. But once we break B down into its perpendicular components, well, then we can group all the horizontal parts, all the x parts, and we can group all the y parts, right, and end up with a right triangle vector diagram, in which we can do, again, a Pythagorean theorem. We've got to add these three, right, together. And then we can do an inverse tangent. Again, add these three together. And we would be able to then name it using either cardinal directions or counterclockwise from zero notation. You with me there? One more little pictorial example for us. What if it was even more complex? What if both A and B were at angles? Well, not really any harder. We just break them both up into their own perpendicular components. If that's our resultant, right, going from the tail of the first to the head of the last, we could break A up into AX and AY, and we could break B up into BX and BY. And once we've done that, gather up all the X parts, gather up all the Y parts, and we have the same resultant, but now in the shape of a right triangle. Watch that again. So we start out with this vector diagram, but if we break A up into perpendicular components and B up into perpendicular components, right, we can then group up all of the horizontal pieces and all of the vertical pieces and end up with one vector diagram in the shape of a right triangle. And again, it's a Pythagorean theorem and an inverse tangent to find the angle at the tail, and then we can name it cardinal directions or counterclockwise from zero notation. So we could do this with two. We could do this with if all three were at an angle other than horizontal or vertical, right? We could do this if maybe it was even more complex and they were overlapping one another and some of them had positive and some of them had negative components, right? We just have to keep track of all of those things. So this method, sometimes called the component method of vector addition, okay, is how we're going to go about adding vectors that are more complex than just horizontal and vertical. So you're going to start out doing this first with a concept builder, okay? This is the form of the concept builder. Took a screenshot of it, okay? It's going to ask you to add some vectors together, and I think I'm going to have you add up to 4 vectors at a time. This one is a little more straightforward. It's just adding 2 vectors, B and D. So you'll notice it's on a grid. Notice that there's a scale for the grid, and that scale's not always the same, so make sure you're checking it out. In this case, the scale is every 1 square is 20 kilometers. I want to add B and D. Well, here's vector B and here's vector D. Now, sure, I could draw B, and then from the head of B, I could draw D, and then I could draw the resultant in, right? But he just kind of wants you to do this using the method we just talked about. So he's given you, as opposed to drawing things out like I did, he's given you a chart to fill in. So he wants you to find the X and Y components of each vector, right? Put them together, and that gives us the right triangle vector diagram. Now be careful, all right? Notice he says here in the directions, you've got to have a magnitude and a direction for your components, and that means a positive or negative sign. So let's run through this one as an example. So B here is completely horizontal. It's to the right, which makes it positive, and it is 2 squares. So if each square is 20 kilometers, yep, this is 40 kilometers. What's the Y component of it if it's horizontal? How much of it is vertical? Yeah, none. So that one was pretty easy to break up into perpendicular components. D is a little more challenging. So here's D. It is 1 box to the left, right? So that makes it negative 20, and vitally important you get the negative on there. And then it is 3 boxes up, or 3 squares up. 3 times 20, a positive 60. So now, mathematically, we're going to do what we just did graphically, which is we're going to gather up all of the horizontal parts, and we're going to gather up all of the vertical parts to make a vector diagram in the shape of a right triangle. 40 and a negative 20 is a positive 20. 0 plus a positive 60 is a positive 60. Right? And these could be positive or negative depending on the components, right? Depending on which ones you're doing here. Well, once you put that in, you'll then click on Check Table. If it's right, he's going to tell you it's right, of course. And then he is going to give you a bunch of vector diagrams, and he says, which one is the right one for this situation? In other words, which one is actually adding up these components? Don't worry about B and D anymore. Worry about the horizontal and vertical components of the resultant. So the horizontal component is a positive 20, which is to the right about one box, right? One square. The y component is a positive 60, which is up 3 squares. So which one of these looks like that? Well, you might say, well, what about the first one? That's to the right and up. But does this look like 20 and that's 60? No. How about this one? Right? Here we have one over and then looks like about 3 times up, right? So it's this one. All of these have issues with positives and negatives. Right? So you got to choose the right vector diagram. And then once you do that, now he wants you to do the trig. Right? And you can do it off to the side and then just type it in. Notice here, though, he wants you to use counterclockwise from 0 notation, so no north, south, east, west here. Okay? So if we do the Pythagorean theorem, we get about 63 kilometers, a couple of sig figs. Usually should work. And then we want the angle at the tail of our resultant, which would be an inverse tangent of opposite over adjacent. 60 over 20. 72 degrees. By the way, make sure your calculator is in degrees and not radians, or you will get this wrong. Counterclockwise from 0 notation, from the positive, is just 72 degrees. This is where this could get a little more complex, right? If we go into some of the other ones, like let's say, we go back to, let's say this one. Okay, let's say this was our vector diagram at the end. It's not, but let's say it was. We would do an inverse tangent and find that angle, but how are we going to name it? Well, we have to remember here, if we put our little crosshairs here, counterclockwise from 0, we start at the positive horizontal. To here would be 90. To here would be 180. All the way around to here would be 270. And then we'd have to subtract this bit to get to here. With me? You'll get it when we get there, but it can be a little harder to name. Yeah, that was my dog barking. And then you'd hit check answers, and he would tell you it's right. So along the way, you're going to check various things, and he'll kind of give you a running total so that you can kind of see that you're doing things right. Notice there's only 3 questions, so right, but they're kind of complex because they're 3 parts. So this is our introduction to solving vector addition problems with computational methods. Notice, though, you still kind of have to draw out some diagrams. Otherwise, how do you really know the answers, right? It's kind of hard to do the trig without a diagram. So I hope you enjoy the concept builder.